Hi everyone, welcome to Unit 3, which is all about applications of the derivative. The last topic that we considered was implicit differentiation, and this allowed us to differentiate multiple variables with respect to each other. And it also allowed us to differentiate with respect to parameters like time. And so this leads us to two very important concepts. One is being able to differentiate an equation, such as a formula from geometry, and the other are myriad applications of derivatives to equations that we derive modeling situations, and that's what we're going to be doing here. The first thing that we want to do is to practice modeling physical situations using calculus notation. And so we're going to go through several examples of doing this, and then we're going to apply this type of rewriting to some applications problems a little bit later in the lesson. But for now, let's just focus on the simpler task of taking a sentence like this and rewriting it. Here we have the volume of a cylinder increasing at a rate of 6 cubic feet per second. So remember that the derivative can be thought of as a rate of change. And so what we're talking about here is a change in volume as a function of time. Now, it really doesn't matter to me that it's a cylinder. That just tells me what type of volume formula I would be differentiating. But all I have to do here is simply write this using calculus notation. And so I'm going to write dv dt equals 6, and this is very important. Don't forget the units. 6 cubic feet per second. And number 2, the depth of water in a rectangular pool is decreasing at a rate of 2 inches per hour. Okay, so we're talking about a change in depth. And so that's going to be a change in height. So we'll call that dH. And again, this is occurring per unit time, in this case per hour. And so this is going to be dH dt. Now the next thing to consider is the sign of this change. Notice that it is decreasing, and since it's decreasing, that means this will be negative 2 inches per hour. Don't forget the units. If you leave the units off on the AP Calculus test, you lose half credit on that problem. Always remember your units. In number 3, they have asked us to model rush hour traffic, and we're concerned about the number of vehicles going through the SunPass toll booth, and it's increasing at a rate of 85 vehicles per hour. And so there's a change in something that is occurring here, and it is a change in volume of traffic. And so I think you could call this different things, but I think dV is probably a very practical differential to use. And of course we're going to use dt to indicate that it is a change per unit time. Now it is an increase, and so that is a positive 85. And I'm just going to write out what it is. Vehicles per hour. Here in number 4, we have air escaping from a spherical balloon at a rate of 15 cubic centimeters per second. So again, we have a spherical shape, and so that would denote a change in volume once again. So dV dt is equal to, and since the air is escaping, the balloon is getting smaller. This is a negative 15 cubic centimeters per second. In the next set of examples, they've asked us to begin with some formulas, and take the derivative with respect to time. So this is going to be implicit differentiation, and we're going to make use of some of the rules of differentiation that we saw in Unit 2. It says, remember to consider which variables change with respect to time before you take the derivative. So the first one they give us is the area of a rectangle, so a familiar formula from geometry. We'll begin by writing the formula A equals length times width. And notice that all three of these can change. And so taking the derivative using the product rule, we get dA in dt. So the change in area as a function of time, dA dt, is equal to, now I'm going to apply the product rule, first times the derivative of the second plus the second times the derivative of the first. Notice that all derivatives were taken with respect to time. Next we have circumference equals 2 pi r. Now remember that circumference is a function of the radius. Pi is a constant, and so I only have two variables here. So c equals 2 pi r. And so the derivative of circumference as a function of time, or with respect to time I should say, dc dt is equal to the constant 2 pi times the derivative of r, which is just dr dt. In number 7, we're back to volume. Volume of a cube, v equals s to the third power, where s is the length of one of the sides. And so beginning with that formula, v equals s cubed, we have dv dt equals, using the power rule, 3s squared, and now I have to differentiate the s, ds dt. In number 8, they give us the lateral surface area of a cylinder. S equals 2 pi rh. S is a variable, r is a variable, h is a variable, 2 pi is my constant. Now again, I'm going to be applying the product rule since we're looking at the product of r and h. 2 pi is a constant, and so I can factor that out. We have ds dt is equal to 2 pi times the first times the derivative of the second plus the second times the derivative of the first. Next we have the area of a circle. A equals pi r squared. So we'll start by writing the formula. And we'll differentiate both sides. dA dt is equal to 2 pi r dr dt. Again, pi was the constant. I applied the power rule to r. And don't forget to take the derivative of r when you're done via the chain rule. In number 10, we have the perimeter of a square. P equals 4s. P equals 4s. And dp dt is equal to 4 times the derivative of s, which is ds dt. Couple of different volume formulas here, cylinder and a cone. So let's differentiate these. We have a v equals pi r squared h, and dv dt is equal to, and I have to apply the product rule here. And so pi is a constant, we'll just leave that there. And r squared, this is my first variable, so r squared times the derivative of the second, which is going to be dh dt. And then we're going to add to that the constant times the second variable, which is h, times the derivative of the first, which is 2r dr dt. And we can rewrite this as pi r squared dh dt plus 2 pi r h times dr dt. Finally, in number 12, we have the volume of a cone. V is 1/3 pi r squared h. That's 1/3 the volume of the cylinder with the same height and radius. And so let's differentiate. We have dv dt is equal to, and I think I'm going to factor out the constant here as pi over 3, and then apply the product rule to r squared times h. So the first times the derivative of the second plus the second times the derivative of the first. And let's see if we can rewrite that. dv dt is equal to pi over 3 times r squared dh dt plus 2rh dr dt. Finally, we have our last two problems here, number 13, volume of a sphere and side lengths of a triangle. So let's take a look at this. Volume of a sphere first is volume equals 4/3 times pi r cubed. Now dv dt is equal to, and notice that 4/3 pi is a constant, and so my only variable here is r. I'm going to apply the power rule, and so that gives me 3 times 4 pi over 3 times r squared. Now applying the chain rule, we differentiate r, dr dt. And of course, canceling the 3's, we end up with dv dt equals 4 pi r squared dr dt. And then finally, number 14, we begin with a Pythagorean relationship, x squared plus y squared equals 25. And differentiating through this equation, we have dx dt. That's the change in the x position as a function of time. So that should be actually 2x dx dt, applying the power rule, plus, again, the power rule, 2y dy dt. And then, of course, the derivative of a constant is 0.